Howdy, my name is Lydia Vidales, and my group members are Vanessa Ramirez, Mario Aguirre, and Nolapat P. Our presentation is about biocompatible materials for implants and prosthetics in biomedical engineering. So what are prosthetics? Prosthetics are made using lightweight materials and contain a custom-fitted socket, knee cuffs, a pylon, and belts that hold the prosthetic and body together. Prosthetics are used by people who have suffered an accident that required an amputation. Chemistry and prosthetics are linked to engineering through biomedical engineering. The main chemicals, compounds, and components involved in prosthetics are titanium and polyurethane. Polyurethane has the chemical equation C27H36O10, which creates a material that has a synthetic resin that is used in the production of prosthetics. Chemistry plays a critical role in the designing and manufacturing of prosthetics, providing knowledge about the structure and composition of the materials. Materials used in prosthetics need to be carefully selected with specific physical and chemical properties, such as resistance to corrosion, being lightweight and durable. Knowledge of chemical bonds and how bonding affects the shape of molecules can provide an understanding of the properties of the substances and the interaction between molecules. This knowledge of chemistry helps scientists and engineers to modify the structure of materials to develop new materials with desired properties. Titanium is a highly used metal in prosthetics. This is due to its many favorable properties, such as its high strength to weight ratio and excellent corrosion resistance. Titanium is relatively unreactive because of the oxide coating that forms naturally when oxygen is present. The oxide coating prevents titanium atoms from reacting with the bodily environment, giving rise to the biocompatibility of the metal for prosthetics. Now, certain materials, however, may not be able to provide enough level of biocompatibility, and thus require modification on the surface. The coating technique can be applied to these materials to increase their biocompatibility, allowing the body to accept prosthetics and not cause any adverse biological responses. Various methods involve using precursors, which are substances that participate in a chemical reaction that produces another compound, to have them react with the materials to produce the coating. Knowledge of chemical bonding is critical to selecting the suitable precursors for the coating reactions to get the result coating. This shows that chemistry not only is related to prosthetics, but also is the underlying principles behind the designing, production, and implementation of prosthetics. Now, here's an example of engineering in dental implants. There are many steps that have to be taken in order to create a dental implant. The implant has to be hypoallergenic, biocompatible, not chemically reactive, and can be corrosive resistant. Metals are mostly used as they are more compatible and can last longer. They have to be able to last when mixing with other chemicals, like in our saliva, and have to withstand the foods that we eat. Titanium and zirconium are used the most when being created. There are other metals that are used, but these are the most frequently used. The implant is created in mainly 3 separate pieces. First, a hole is made where the tooth should be. Then the root post is placed inside the gum, and then time is given to let the post heal with the gum. The root post was made to be small and fit as perfectly as possible in the gum. Before inserting, the dentist has to be sure that the metal is used can be safe and sustainable. Then, an abundant insert is placed so that it would be nearly difficult for the tooth crown to be removed. It also helps to support everything, and if anything needs to be changed, it would be able to be replaced easily using proper tools. Now, the future for biomedical engineering. Future innovations are going to focus more on advances in surgery and engineering, and focus more on amputees' demands. The prosthetic technology has advanced tremendously, and are highly driven by the amputees' demands. The most crucial aspect of a prosthetic is the quality of the interface between the prosthesis itself and the stump. The future of prosthetics is leaning towards ligament advanced reinforcement system artificial ligament, also known as LARS. The LARS artificial ligament consists of fibers made of polyethylene tetraphthalate. The future of prosthetics, which is an intraosseous segment that is composed of longitudinal fibers that are bound together by transverse knitted structures. The future of biomedical engineering is focused on regenerative medicine, biomaterial, and tissue engineering. Engineers are combining knowledge in cell and molecular biology, physiology with biomaterials, biomechanics, and biotransport phenomena. This regenerative medicine is aimed to understand the structural, biological, and mechanical processes that are used in developing systems to repair or replace damaged tissue and organs. The future of medical engineering is looking bright for amputees and possibly a future in artificial ligaments. Thank you for listening to our presentation, and I hope that you learned a lot and enjoyed it.